Well, now let's take a look here at example 6. In example 6, we'll see that we still don't really actually have something that we can use L'Hopital's rule on immediately, because certainly we can see that we don't even have a single fraction here at the start. We have two separate fractions, and if we were to try to evaluate each of them individually, we could notice that this 1 over x piece here is going to be moving towards positive infinity, and this 1 over sine value here, notice, is also going to be moving towards a positive infinity. The reason I know this is because sine of 0 is going to be approaching or sine of x as x approaches 0 is going to be approaching 0, and 1 over something approaching 0 is going to be infinitely large. So what I have here is an indeterminate form of an infinity minus an infinity. If you were to look back at that box of indeterminate forms on the very first page of this notes, you'll see that this is up there, I believe, as the fourth item inside of that box. It's another indeterminate form, but not one that I can use with L'Hopital's rule. But we're ultimately going to have the same goal here as we have in the past two videos. Can I maybe get this awkward indeterminate form to kind of fit one of the indeterminate forms that I know that I can work with? That is 0 over 0 or an infinity over an infinity. So one of the first steps that I might be able to do to get there is to maybe try to get all this to actually look like a single fraction. So I'll start by saying, note that my limit as x approaches 0 from the right of 1 over the sine of x minus 1 over x could be rewritten as a single fraction if I got a common denominator between these two things. So I could have x over x times the sine of x minus the sine of x over x times the sine of x. There we go. So if I pushed this together to make a single fraction, notice all I'm doing here is just some basic algebra, then I could end up with the following. Now, this is at least a single fraction, so there's a chance that L'Hopital's rule might work, but of course I still have to check to see that I have one of the appropriate forms. So let's check to see what happens with the top and the bottom. If x is approaching 0, then this numerator is going to be 0 minus 0, so that's 0. The denominator is going to be 0 times 0, which is 0. That's perfect. I can now actually use L'Hopital's rule. And so I can go ahead then and state down here that I'm going to make use of L'Hopital's rule, continuing on, of course, from this line. So if I take the derivative of the top, no big deal. It's a little bit messy up there, but I'll just do the derivative, again, one term at a time. So I'll start by taking the derivative of x, which is 1, and the derivative of the sine is the cosine. Ooh, notice though in the denominator, I'm going to have to make use of the product rule because I do have two items here being multiplied. So I'll go ahead and say derivative of the x is a 1, and I'll leave the sine of x alone. And then I add and reverse the order. I'll leave the x alone, and the derivative of the sine of x is the cosine of x. Okay, so here again I have a nice big messy function. Let's see what form it's actually in. All right, so the numerator here is going towards, let's see, 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. In the denominator here, I'm going to get 0 plus 0 times 1. So again, I'm going to get 0. Well, then I could use L'Hopital's rule again, since I have this form 0 over 0, and I don't see any way I might be able to easily simplify this by like factoring something out or anything. So let's try L'Hopital's rule again. So I'm going to get a limit. X approaches 0 from the right. Here I'm going to get 0 minus negative sign. So I'm just going to end up with a positive sign up top. In my denominator, derivative of the sine is the cosine of x. And notice, oh, darn it, over here I'm going to have to do another big product rule. So I'll take the derivative of the x, that's a 1, and I'll leave the cosine of x. And then I'll add and reverse the order. I'll leave the x alone and take the derivative of the cosine. So if I leave the x alone, the derivative of the cosine should be negative sign. So instead of putting a plus sign to connect these, I'll put the minus from that derivative right here. Okay, so here's another thing now that I have to try to work with. Let's see. The numerator here would actually be going towards 0. My denominator would be going 1 plus 1 minus 0. So my denominator here is actually going towards 2. Oh wait, 0 over 2. I could actually compute that. I don't even really need to state this. I could jump right to the actual evaluation. This is going to be 0 over 1 plus 1 plus 0. That's 0 over 2, and 0 over 2 is a value that I know. That's just 0. So I can see here that now I ultimately have evaluated this limit. And the goal was essentially the same. If I don't have one of my original nice forms that L'Hopital's rule can work with, I'm going to go ahead and try to manipulate what I have until I have one of those forms, and then apply L'Hopital's rule and some basic algebra to try to go ahead and arrive at a final answer.